We're going to talk about the extreme value theorem, and this is going to be one of the first few theorems in this chapter that's named. So you want to you don't have to necessarily recite it, but you need to know what it means and how to use it. So the extreme value theorem tells us that if a function's continuous on a closed interval, then it's guaranteed to have an absolute maximum value and an absolute minimum value in that interval. So remember, we had looked at an example of a function that did not have any absolute extrema. So we looked at f of x equals e to the minus x. And the reason that the extreme value theorem doesn't apply is because this is not a closed interval that I defined this on. Its domain is an open interval, minus infinity to infinity. But if you have a closed interval, then you're guaranteed to have a maximum or a minimum. Absolute maximum or minimum, excuse me. So if you look at this graph, notice that the right endpoint is open. So this is not closed on both sides. So even though it may look like this point is higher than all the others, there's a hole there. So this is not an absolute maximum. And so this graph does not have an absolute maximum. This function doesn't have an absolute maximum. So another thing you need to notice about the extreme value theorem is it just talks about absolute extrema. It doesn't talk about local. Before we looked at f of x equals e to the minus x and its natural domain. Now if we restrict the domain to, let's say, minus 2 to 10, a closed interval, now we can see it does have an absolute maximum. Let's take a step back for a second and think about this function, e to the minus x. So all the y values are continually decreasing as we move along the x-axis to the right. It's a decreasing function. So that means that a maximum is going to be at the leftmost endpoint, and a minimum is going to be at the rightmost endpoint. And that's because this is a strictly decreasing function. Likewise, if it were a strictly increasing function, the minimum would occur at the left endpoint and the maximum would occur at the right endpoint. This example doesn't have any local extrema here because the absolute extrema occurred at the endpoints. And remember, a local extrema can't occur at the endpoints because you don't have a neighborhood on either side of the point. So the notice that the extreme value theorem doesn't tell you how to find the absolute extrema, just that they're guaranteed to exist. So we can identify them graphically, but we're going to need to know how to do more than just identify them graphically. So we're going to see that because local max and mins, local extrema, can be absolute extrema, that's a place to start looking for our absolute extrema. There's one more thing that we're going to talk about first before we talk about exactly how you find absolute extrema, though. So for Matt's theorem, you don't need to memorize or recite. Just know what it means. If a function has a local maximum or minimum at some value c, and if the derivative is defined at that value c, then f prime of c is 0. So this doesn't say that necessarily where a function's derivative is 0, it's necessarily a max or min. It just say if it has a max or min, then the derivative is 0 there. So that's different meaning. So it's just kind of going in one direction. So, for example, f of x equals x cubed. There's this red graph here. Its derivative is 3x squared. And you see that its derivative is 0 at 0, right? 3x squared is this blue parabola. So its derivative is 0 there, but obviously on the original function x cubed, the origin is not a max or min. So that's why the converse of this is not true. So this kind of gives us this definition of critical numbers, and you may be familiar with these from pre-calculus and some other contexts. So a number c such that the derivative evaluated at c is 0 or doesn't exist is called the critical number of the function. And that's because things happen there at those values. Things will be happening on the graph at those values. So again, looking at this cubic, I moved it over 3 just so I could fit both graphs on here nicely. Looking at this cubic, at x equals 3, the derivative is 0. So that's a critical number, but again, it's not a max or min. And here at 0 for the absolute value function, the derivative doesn't exist. And notice that it's that corner. So that's another example of a critical number.